So should I start the intro a little bit? I just want to make sure they can hear my audio.
Okay, I can set you up with this lapel mic.
Oh, thank you. Hello.
Just put it in your pocket. Put this. Close to your hip. Grabbing all of it so that people at the back voice can.
Good morning, everyone. Welcome to the 2025 Vision Forum. My name is Chang An. You can also call me Leah. I'm currently a PhD student from Carleton University School of IT under the supervision of Dr. Chris Joslin. So it's my pleasure that I'm going to run the very first session of this of the day, student presentation, where students from our program will be presenting their research or internship experience. But before we get started with the presentation, please allow me to give you a very brief intro about Vision. So Vision is an insert create industrial stream program. Its goal is to build bridges between industry and academia through program-sponsored internships, providing students and graduates with the skills they need to succeed and lead in Canadian industries. Vision focuses on visual effects, animation, graphics, film, and TV. And its research spans across many fields, from data science and AI to computer science, human-computer interaction, UI, or user experience design and fine art. So for our schedule of the day, now we are having this very first session, student presentation. After this, it's going to be the lunch break. And there are two industry discussion panels in the afternoon with a coffee break in the middle. And starting from 3:45, it's going to be our visionaries faculty research presentation. All right, so it's almost time for the presentation. For the presenters, every one of you will have 5 minutes for the presentation. We have presenters from both on-site and online. And Joy and I will help you count the time, and when there's only 1 minute left, we will give you a sign so that you know it's time to wrap up. And at the end of each presentation, you will have 2 to 3 minutes for questions. But if the presentation is longer than 5 minutes, I'll probably just move on to the next presenter, making sure we're on schedule. Okay. So please allow me to be your warm-up presenter. We have So, my research project during my PhD centers around 3D facial animation and retargeting. And this is going to be the topic I'm sharing with you today. All this research, they are supervised by Dr. Chris Joslin. So why do we care about 3D facial animation? Why it's important? As you might have experience playing games, watching films, seeing advertisements, and interacting with immersive systems such as VR and AR, you're witnessing this expanding influence and applicable scenarios of CG character, where the 3D facial animation makes a big part of their performance, and it's also a major component of the storytelling. But traditionally, when we are animating a 3D face, it's very time-consuming because the animation is either done frame by frame or pose by pose. And there's a frame rate ranging from 24 to 120. So it's a very labor-intensive process. And that is where facial motion retarding comes in. Just as the name implies, retarding applies the motion data from motion capture to the 3D faces of characters. Examples that you are probably familiar with are from, for example, Avatar: The Way of Water, a recently very hot game, Black Myth: Wukong, Red Dead Redemption 2, and The Last of Us. So the advantage of retarding is that it transfers the subtle facial dynamics to the 3D characters and enables fast and high fidelity facial animation. But retarding pipelines available seems not providing as much assistance to the industry as we expected. According to the leading edge studios such as Industrial Light and Magic, Weta Digital, even with motion capture used, they still have to perform a large amount of keyframing and manual adjustments when they are producing their characters, especially for those that are fictional, that do not have a real life reference. In other words, existing retarding pipelines struggles at providing accurate reflection of the source motion, especially for less human-like characters. It needs 3D scans or blend shapes for rigging the target face or guiding the retarding, where both of them are time-consuming to acquire. So our research focuses on exploring a new retarding pipeline to enable fast and high-quality facial rig, and also providing reliable motion analysis and appealing facial animation. Of course, we want the pipeline to work for diverse characters. So as the very first research during my PhD, I did a thorough review on available retarding methods. And this forms a survey where the survey describes the relations and connections of the essential modules of a retarding pipeline, providing a taxonomy on 3D characters, retarding methods, and relevant topics. Also, the survey explains the reasons behind the advantages and limitations of existing methods. This survey has been published at the journal Computers and Graphics. So after we gain this understanding of the existing retarding pipelines, we started to design our own. And this becomes the second research of my PhD, where we design a retarding pipeline for diverse characters. And we formulate the retarding problem as a parameter transfer problem that consists of two modules, a motion analysis and a face rating module. And this work has been presented at CGI 2024 in Geneva, Switzerland, and also published at its relevant journal, Computer Animation and Virtual Worlds. So one of the highlights in our research is this 3D face parameterization or rigging method, inspired by physics simulation and face anatomy. So this method is independent of face-specific blend shapes. It presents natural and accurate expressions across different characters. Its parameterized faces can be easily edited and driven by motion capture data. And one of the biggest innovations is that we utilized position-based dynamic cloth simulation for physics-based properties of the facial muscles and fat. And we created a video for this paper, so I'm just gonna quickly show it to you. It doesn't have an audio. So this is the video showcasing the physics-based effects and retarding results from the face rig that we built. It's an anatomy-based method. So we can see these muscle abstractions and fat abstractions, and also the physics effect. And this work was luckily being accepted at SIGGRAPH Asia 2024 in Tokyo, Japan. And we also would like to thank Dr. Eric Beckett for his insightful review and feedback during our rebuttal stage. Last but not the least, it's the most recent research project that we did, where we focused on analyzing the facial motion, because as we mentioned previously, facial motion analysis and 3D face reading are two essential modules in the retargeting pipeline. And in this work, we proposed a new motion representation for a semantic reflection of facial motion data. We call it motion units. And also we designed a region-based motion analysis model for regressing the 3D landmarks data and the new motion representations. And this work is currently under review. So over the years, we have done a lot of in the lab motion capture with the students, with the volunteers, and it was so much fun. And also in the wild conference attendance that we really enjoyed and allowed us to travel to different beautiful cities. And yeah, we are excited to see how Vision will lead us in further exploring the road of CG and VFX. Thank you. All right, so I think I have two minutes for questions. So if you have any questions, both from online and on site, I'd be happy to answer. Okay, if not, I'll just move on to our next presenter, Vincent Alex Jolie from ETS.
Full screen or okay, but then setup. Okay, cool.
Microphone, put it in a pocket and put it on your coalition. Right.
Is it fine?
Yes. Awesome.
Thanks. Should I go now?
Yeah, go ahead.
Perfect. Okay. Hi. Thanks for presenting me. I'm Vincent. I come from ETS's multimedia lab. My master's student. I'm supervised by Dr. Eric Paquette. And my work centers on smoke reconstruction. So as you may know, games often use crude position and velocity-based particle systems to approximate smoke. Even cutting-edge games such as even in cutting-edge games like The Elder Scrolls 4 Oblivion Remastered, which is pretty much the prettiest game I've ever seen. Like when it still looks fake. You can see the repeated texture particles. When you move your camera out of view, the particle emitter stops. Snap back your view, it begins again. Super jarring. On the other side, like fluid simulation is as long computation times and large memory requirements. A simulation cache for a few frames can be gigs. During a previous internship, I was introduced to 3D Gaussian splatting, and I believe that it could be adapted to bake simulations to a more digestible format for real-time rendering requirements, thus lowering the cost of simulation and allowing better smoke and more games. So for those unfamiliar, 3GS is essentially a method that takes point clouds and cameras, transforms point clouds and the points into essentially football balls that you can squish, recolor, deform to try to fit the appearance of the scene through simply a differentiable rasterization process. The advantage of Gaussian splatting compared to NeRF and NeRF-based methods is that your Gaussians exist in 3D space, so they can be manipulated with transformation matrix, just like you would if you were manipulating vertices. And I think those properties would allow this a method based on 3D Gaussian splatting to break out of labs and enter production VFX pipelines. At the moment, even the base method can reconstruct smoke pretty okay. like when you can see on the left side the ground truth as a simulation I did in Blender. Compared to its 3D reconstruction with Gaussian splatting, and you could probably fool non-VFX people, but you can clearly see the smoke is more blurry. The puffs don't quite line up, and I'm trying to improve that. So my contributions center around two poles: better capturing the fine details of smoke, and then trying to, with these better captured details, use the reconstructed scenes with other scenes, just like you would with a Vertex, a 3D edition program like Blender. So one of my first experiments was trying to render the scenes against two backgrounds. By default, it only renders against either a white or a black background. You get quite heavy background bias, like the point cloud doesn't quite learn the difference between your transparent objects and the background, so you get your black spots in your capture, which breaks the illusion when you combine the things together. And for the same end, I'm trying to do densification scheme characterization, try to identify which points aren't lining up with the main subject. So hopefully to make either learn that those are good or straight up cut them as a post-process step. I also try to automatically detect smoke through its appearance, trying to find the gray. For instance, if we know that the smoke is gray, then we can try to identify grayish pixels and force them to work to optimize an opacity versus and restrain their color. That's a work in progress. That's not working too good at the moment. And then scene compositing. Well, I already talked about my background debias. But at the moment, you can load multiple scenes together. You apply a rotation matrix along the z-axis, get teapots that don't destroy each other's appearances, and the smoke is pretty much as you'd expect, like the vapor coming from the teapots, maybe a bit too opaque for vapor, but the transparency is okay, is well handled. But the thing is, there's issues with the representation. Gaussian splats are stocked as a position, a rotation, a scale, and a spherical harmonic color. And while there is literature on rotating spherical harmonics, I think for those that aren't aware, spherical harmonics is you encode the color, the appearance of the splats through a unit sphere. It's a basis function that allows to reduce the frequency of a light capture. And a rotation of such a function is typically on the complex plane, so there are difficulties getting that to work real time, as you get these massive rotation matrices. So yeah, that's I'm working on something. So that's pretty much my work. Thanks.
Thank you. So do you have any questions for people?
I'm not sure.
Like admit that.
Let's zoom.
So I actually have a quick question, a very, like, this is not my area, but I'm just
Sure.
interested. So what are the potential applicable scenarios of your work? Like in VFX or film or games?
Well, yeah, I hope it could be used in games and real-time apps. Uh, uh, well, I kind of the stress made me gloss over that detail, I guess. When for instance, when you do when you try to export a smoke simulation, you do it with these density grids or huge files.
Mhm.
Like if a few frames is like 1 minute, for instance, can be 2 gigs, and
So it's lighter weight.
so
simulation.
yeah, when we do reconstruction Gaussian spline for the same data, you can get an output file that is maybe 5 megabytes per frame.
So like much less
So
memory. use.
about maybe at least 2 times more space efficient,
Fantastic.
and many more times faster to render.
Awesome.
Like instead of getting a frame every few seconds, when you do the simulation, you can get 400 FPS on decent hardware.
That's very cool.
Thanks.
All right. Yeah. So do we have any other questions from online and from on site? If not, then we will just move on to our next presenter. Thank you, Vincent.
Thank you.
All right. So let's welcome our next presenter, Quinn McGill from University of Ottawa. Quinn is from online.
Sorry, yes, I think probably the easiest way for me to do this would just be to share my screen, but let me know if that doesn't work.
How can we turn on the audio so that all the can hear?
Probably the easiest way for me to do this would just be to share my screen, but let me know if that doesn't work.
You should be able to share now. You try it again.
Okay.
Should be able to share now.
Are you able to see my screen?
Can you hear us, Quinn?
Sorry, can you see my screen?
Yes,
Yes.
we can see your screen.
Okay, perfect. Then I think I should be okay.
Can you hear us, Quinn?
Sorry, can you see my screen?
Yes, we can see your screen.
Okay, perfect. Then I think I should be okay.
Can you hear us, Quinn?
Sorry, can you see? Okay. Sounds good. We'll come back. Got it.
Hello, hello. Yeah, I think this one
Okay, yeah, now.
works, right?
Okay,
Okay, fantastic.
okay. It's just,
Hello, hello. Yeah, I think this one.
oh, okay, now it's
Works.
Apple. Oh, yeah, Apple. We just muted.
Yeah. Yep, you can mute it because originally we turned it on for music. For audio.
Okay. It works, it works. All right, hi everyone. My name is Terry, and I'm going to be, oh, these are old slides. Wait, this is not the right version of the slides.
No.
No, I sent a different version to Joy. This is the version I sent to Leslie.
She's well, Joy's not right, not here. I don't think she updated it.
That's fine. I might still be able to work with these.
Okay, if you prefer, maybe I can.
No, I'll just work with these.
Okay, sorry.
All right, sorry for that. Hi everyone, my name is Terry, and today I'll be talking a little bit about both my research, but also just about my experience doing a research internship. So a little bit about research, but also my experience doing a. Okay, there we go. Come on. There we go. So a little bit about me. I'm a second year master's student, supervised by Professors Adrian Gruson and Professors Derek Noro-Zazari. I do research in rendering, which is the science of basically turning a 3D scene into an image. And this past year, I did a 9-month research internship at Ubisoft La Forge, so the R&D division of Ubisoft. Previously, I was a USRA researching solvers for general partial differential equations at UWaterloo. So I have a research internship experience from both the academic and industrial side of things. My research specifically focuses on solving the problem in real-time rendering, solving problems in real-time rendering of improving image quality. Real-time rendering is kind of the encompassing field of rendering in game engines, or anything that basically the image is output now and now and now. So in the context of VFX and film, we see this more and more in virtual sets, which are those kind of like big light boxes that you might have seen used on The Mandalorian, or more so nowadays in indie animation, which is increasingly relying on game engines like Unity and Unreal to output their films and whatnot. In my research, we have the problem where given mirror-like surfaces, we tend to have a poor image quality. And so my research is focused on the idea that if we do a little bit of fudging to the mirror-like surface, we can have an increase in image quality basically by increasing the amount of information that is available to us. And more information and more quality information means better results. So here are some of the preliminary results that I have. They Basically, if I don't know how well it shows up there, but you can see that there's a decreased noise on on our method and increased fidelity of the output image. So now I'll talk a little bit about research internships, what they are, what they aren't. Research internships, like the name suggests, it's an opportunity to do research in this kind of a short-term internship setting. You get to work with a R&D project, and more so, you also get to collaborate with experts that are outside your immediate academic sphere. Whether you're in a lab or an industry, you'll be working with PhDs, distinguished scientists who can offer you different perspectives, oftentimes either from their own PhDs, which may be slightly different from your work, but close enough that they can still work with it. In any case, it's a great opportunity to just broaden your perspectives on your general research problem. It's also a good chance to pick up new skills. So for example, going into Ubisoft, I knew very little about the practice of real-time rendering, but I was able to learn a lot about working with the game engine, working with like low-level graphics APIs during my time there. And as always, if things work well, you get a chance at publishing a paper. Of course, what they aren't, research internships are structured a little differently from your traditional co-op or internship. If you've done that during, say, your undergrad, you're not really working off of tasks or tickets. You're not really like focused on, say, a Jira board where you're trying to clear the backlog. But it's also not like completely free. It's not a free-ranging sandbox for ideas. You do have a project. You do have to stick to that project. And lastly, it's not guaranteed extra money. Oftentimes, the stipend that you get for your research internship, that's just part of an existing funding reward. So my experience at Ubisoft was, first of all, I quite enjoyed it. We had a very close collaboration between my supervisors academically and also my colleagues at LaForge. We would do two bi-weekly meetings, and this was an opportunity to just keep everyone in the loop on with regards to progress, setbacks, etc. And also just a great way to soundboard ideas off of each other whenever the project got stuck. And this was also an excellent opportunity personally for me because the project I worked on was at Ubisoft. I'm able to use that towards finishing my thesis. Time structure wise, the first 2 weeks or so, that was just onboarding and a bit of starter project to get me up to speed with Ubisoft's infrastructure and their frameworks. The next 2 weeks, we spent kind of just like nailing down our project, like what we wanted to work on, and kind of what we saw would be a good fit for my limited time there. And after that is just your traditional, you prototype, you validate the results, and you repeat and you refine your research. So kind of just to summarize everything, industrial research internships, you're able to experience industrial research, which is quite a different perspective from the academic side of things. Usually, there's more practice. You have these kind of additional constraints. So for example, in academia with computer graphics, usually we're not too concerned about performance, but in the real-time industry, you have to run at 60 FPS, so that's 16 milliseconds to generate your image. And for rendering specifically, they aim at like 30% of that, so less than like 7 milliseconds to generate your image. So it's a very interesting problem. You have lots of resources, you have your supervisors as well as additional colleagues. Of course, a bit of cons is that you have less flexibility in your choice of research project, because it's whatever the company wants, whatever direction the company wants to go for. So you have to follow that. And you got to balance company versus academic priorities. So for example, I had to sign an NDA. Lots of people in industrial research may not be able to put their project towards a thesis or even just a paper. A lot of times just stays confidential. But overall, I would say if you're a student and you get the opportunity to do a research internship, you should try it. If you're someone in the industry and you have an opportunity to take a student on for a research internship, I also suggest you should try it. Thank you for your time. Thank you for listening. And if you have any questions, I'll be happy to take them.
Do you think that it would be valuable to basically bring on board interns for research, even though the company doesn't have a research department or research?
That's an excellent question. I think I would say in that case, I would say like in that case, I think it depends on like who's supervising. If someone's, because I would say you don't need an R&D department to do research. But you do need someone who knows who knows kind of like the research pipeline, who can probably navigate both like the administrative, like just able to navigate like administration as well as like research and academia. So like I would say like probably you could have like one like say like supervisor who has a PhD who has an interesting research idea that they can turn into a research project for an intern and not have to set up a full.
So, Ihib, I noticed you just joined us. But before you, we still need to let Queen to present because previously Queen run into from our side we run into some technical issues, so Queen wasn't able to share the screen. So Queen, are you ready to present?
Yeah, I can present. We'll see how it goes this time. Okay. Okay, can you see my screen? Perfect. Okay. Okay. So my name is Quinn. I'm a graduate student at the University of Ottawa, and I'm going to just briefly go over a bit of my co-op experience so far. First, a bit about my background. To give you some context, I did my Bachelor's of Computer Engineering at Queen's University, and I graduated last May. I am doing my Master's of Electrical and Computer Engineering with a concentration in Applied AI here at the University of Ottawa. I actually only started in January of 2025, which means I've actually only had one semester of classes so far. My research area is in the intersection of AI and then animation and VFX. And I have two co-supervisors, Chris Joslin from Carleton University and Jochen Lang from the University of Ottawa. Making sure everything is lined up. Okay. So I actually only started an internship about a month ago on June 20th, and I'm working at a company called Neural Edge. They are a Canadian startup company that's located out of Markham, Ontario. Currently, what they do is they provide secure, dedicated GPU infrastructure built for enterprises, researchers, and developers. They have access to really high-performing computing power. What they currently do is they offer like a GPU as a service. But what happens is if the GPUs aren't rented, they just sit idle. So they're looking for projects to run alongside that GPU as a service. So what they're actually looking into is some projects in the TV and film industry, but these are very much in the early stages of development and they're still planning them. Currently, what they're working on is benchmarking their GPUs for rendering to see their speed. One project that they're looking at right now is this on-the-fly set planning tool. The motivation behind this is that there's a lot of time spent setting up each scene during TV and film. So that's dedicated to setting up lighting rigs, set design, things like that. And it means there's a lot of like downtime on set that could be used more productively. There's also changes in shoot planning that can result in really long shooting days. So their goal is to create a tool which does a 3D rendering of sets using a LiDAR scan. And then they're going to create a model of the setup and offer that to directors, which they can access through like iPads. And they will be able to model lighting setups and then plan their shots in advance. And this is to overall improve shooting day efficiency. So there's less downtime and it's spent creatively. Another project idea that they're looking into is AI-assisted mocap cleanup. So in traditional mocap, you have cameras which are capturing the light reflecting off of mocap markers in order to track the movement. Oftentimes these markers can be blocked, which means that you're losing position in 3D space. And the cleanup process is hours long by really professionally trained or especially trained cleaners and professionals. And this can really slow down that pipeline. Their goal is to create an AI model which can speed up this process by filling in gaps and picking out mistakes. And this is going to be really important for industries like game development, where mocap is so important. And then the final project idea that they have is this AI-assisted crowd simulation. So this is for cases where large groups of characters need to be generated and animated whenever using real extras would be really impractical. This is to improve the realism of things like battle scenes or really large gatherings or really crowded city streets. The goal would be to create tools which use AI to animate the crowds based on dynamic context. So you can think of an example as like at a sporting event, if one team scores, which crowd members are going to cheer and be excited, and then what crowd members are going to, boo or just look dejected. So those are some ideas of projects that they're in the beginning stages of planning. Thank you so much. That's it.
What about now? What about now? Oh, fantastic. Thank you very much for the presentation, Queen. Sorry about the audio issues that we had previously. Okay, so given that Ihib is with us right now, Ihib, are you ready for the presentation?
Yes, I'm ready.
Okay, fantastic.
Can you hear me?
Yes, we can hear you nicely. And do you want to share your screen?
Yes. Wait a minute. Can I start now?
Yes, please go ahead. We can see your screen.
Thank you. Hi, hello. My name is Ihab Rashdi. I'll soon begin my master program at ETS, supervised by Mr. Eric Bucket. Today, I'm going to present Unity assets I recently developed that handle real-time animation. One of its key features is a lightweight bending system designed specifically for deforming paper-like meshes such as cards, leaves, etc., in a realistic and efficient way. Now I'll explain some key design choices that I made uh, behind the bending system that allow it to bend many objects without lowering the frame rate of the game. The mesh deformation is fully handled on the GPU side. The CPU doesn't modify the mesh, it's only send the simple animation data like time, position, and direction. The shader code doesn't use any branching loop or conditions. Everything is done using mathematical functions, which help to keep it fast and smooth on all devices. The system also preserves the distance between the vertices, so the mesh bend naturally without breaking or stretching, and that will prevent the deformation of the textures. I've developed two systems for the motion-based bending. The first one is called raw motion. It simulates curling or rolling effects. This allows the developer to bend the mesh in real time in any direction or shape they want. The developer just define the target bending system like the pivot point, the roll axis, and the radius of the bend. And the system handle the animation automatically with smooth tween transitions. As you can see in this example, the system preserves the surface integrity. There is no distortion or stretching in the texture mapping in all the bendings. Now for the second bending system is called spline motion. In this motion, the mesh move along a given spline and bend in real time to match the curvature at every point in the spline, in the Bezier curve. While the CPU's role is minimal, it does provide the GPU with a single float value, each frame that represent the card current position along the spline. The GPU takes care of the rest, bending and animation, and animating the mesh based on the position using mathematical function with no branching or loops in the shader. As before, surface integrity is preserved. There is no texture stretching or distortion like you see. As a bonus, if we straighten up the spline and rotate its control point, the system creates a twist effect motion. As shown in this example, the card is twisting over time. Now, for the motion manager, it's the core system that controls how the objects move and animate over time. It's allow custom motion behavior where a new motion type like spline, roll, or custom animation can be easily plugged in. It supports multiple playback modes and provide tween functionality. You can play, pause, continue, kill, or append motion in a sequence of chain, giving developer full control over how each card moves frame by frame. Here's a small code snippet that show how easy it is to plug in different motion type and process them in a shape. Each motion is fully configurable, and the motion manager takes care of chaining time and blending between them. I have a video, if I can just share it with you. Okay, here the video that show the system in action. each card doing one motion, starting from the right card is doing a wheel motion, followed by a spline motion. As you can see, there is the second card is bending through 3 basic curves. The fourth card is doing a random bending and curling motions, and the fourth one is twisting motion. Uh, that's it. Thank you for listening. If you have any question, I'm happy to answer.
Thank you very much for the presentation, Ihib. Do we have any questions from on-site for Ihib? No? Do we have any question from online? Okay. If not, let's welcome our next presenter, Haidan Liu from Simon Fraser University. Haidan, I believe you're presenting remotely, so you can share your screen whenever you're ready. Haidan, we can not seem to hear from you.
Sorry, can I have 1 sec? I don't think let's see.
Okay, we can hear you now. But it looks like your screen is very small. Is there a way for you to zoom it in?
Um,
Are you sharing from YouTube or from Zoom?
from Zoom.
Okay. Ihib, do you mind like stop sharing your screen? I'm not sure if that's influencing the screen size.
Do you think it's possible for me to stop sharing and then reshare my screen?
Sorry, can you say that again?
Let me see.
Can you say that again?
How about now? Can you say now?
Not really. It's still like very small. Oh, it's much better.
It's much better.
Yes, yes.
Oh, okay, great. Sorry for this trouble. Can I get started now?
Yes.
Oh, thank you. Hello everyone. Today I'm gonna presenting a project about how creators are navigating the confusing world of AI image generation. A little bit about me. I'm a second-year PhD student at Simon Fraser University. Work with Dr. Pramit Lanan and Dr. Nick Vicent. So let's start it with a story. Imagine you are a talented artist. You are so talented that you have won every prize everyone could even dream of. But no one is perfect, and you only have one flaw. You don't know much about machine learning. You're working on a delightful story about a family of turtles having tea in a mossy forest, and you turn to AI for help. Just want to get a quick visual idea. But every time you run it, you get a weird turtle. The turtle's eyes are on its back every single time, no matter how many carefully you write the prompt. So you might think, okay, I will check the tutorials. Maybe they can explain what went wrong. But instead, they tell you to adjust your CFG scale or refine your negative prompt. Unfortunately, none of those actually make sense to you. And now you are stuck with 27 cursed turtle image and a growing existential crisis. You didn't sign up for this, you are not an engineer, and you just want eyes on the face. So this is when the project began. We saw talented creative people who turned to tutorials for help, only to crash into technical walls built out of terminology that assume everyone spoke fluent in machine learning. And it turned out this wasn't just one person's frustration. We surveyed 159 creatives to figure out one key question: how helpful are current tutorials for learning AI image tools? And 1 in 3 said the tutorials were not helpful. Life was even harder for those without any technical backgrounds. About half of the non-technical users found them overwhelming. So what is stopping people? It's not the motivation, it's the language, the terminology. One response actually said, copy and paste the settings, like all the settings in latent modifier integrated. What does that even mean? So we created another simplified tutorial called Pickbox. It's a comic-style interactive tutorial that explains AI concept without jargon. We developed it through rounds of feedback, first from artists, and then from machine learning expert. The final version of it covered text to image, style transfer, and sketch to image. It's straightforward and it's engaging. And most importantly, it meets people from where they are, not where the tools assume them should be. And then we put Pickbox to the test. We ran a user study with 17 participants. Most had some experience using generative AI image tools, but none of them actually machine learning expert. And each participant completed 4 creative tasks using one of the 2 approaches, one with a tutorial and the other one with self-experimentation, basically trial and error. And here's what happened. With Pickbox tutorials, participants generally image that were more aligned with their original ideas and they feel more satisfied. And they rated the tutorial as genuinely helpful. Sounds like a happy ending, right? But not quite. While participants actually appreciate the help, many also said they didn't want to be told what AI can or cannot do. They felt that the guidance was useful, but sometimes it got into the way of their creative freedom. When participants actually said most of the time, I don't really like to be guided when I'm doing things like creative. And that's not all. We also uncovered some common misconceptions. Some participants believe that AI was simply just searching the internet for images, and they often feel overestimated their understanding of how AI works, and when their output didn't align with their intention, they often blame themselves. They assume that the issue was with their wording, believe that AI had already done the best it could. And why we want to do this kind of project? Because many of the people actually trying to use these tools, they could be creators, curious first-comers, beginners. They don't have any technical background, and they actually shouldn't need one. If generative AI image tools is meant to be used by creative expression, it should be approachable to the people who actually use it. And that's all I have. I'm happy to take any questions. Thanks for listening to my presentation.
Thank you, Afra. Do we have any question for Afra? Okay, so I don't think we have any question from online. Thank you very much for your presentation, Afra. Okay.
Thank you.
Thank you. So let's move on to our last presenter, Kanak Gautam from Simon Fraser University.
Hi everyone. I just want to make sure, are you able to see my screen?
Sorry, can you say that again?
Hi, are you able to see my screen?
Yeah, we're seeing your screen.
Okay.
Yeah.
So, hi everyone. I'm Kanak, and I'm a first year's master's student at SFU, and I am working under the guidance of Dr. Parmeet Chalana, and I'm exploring a space where creativity meets AI, a 3D modeling space. So, but instead of focusing on AI tools themselves, my research looks at how different people use those tools and what that tells us about learning, design, and interaction. So imagine you've just discovered a new AI tool that lets you generate 3D models with a few clicks. Sounds amazing, right? But how you interact with this, what do you expect from it? It might look very different depending upon who you are. That's what our research is about. The AI is same, but the way the users approach is it's very dramatic. Now picture yourself as a casual user. Maybe you are a student or a hobbyist dabbing in 3D design for the first time. You open the tool, maybe type a prompt like futuristic chair, and wait for the magic. You are experimenting. You might Google how to write better prompts or click around to see what happens. That's excitement, but or that's also a confusion. The tool feels powerful, but you are not sure how to get what you want. You look for hints, examples, or just try things until something works, right? Now shift roles. Imagine you are a professional. You have worked with CAD tools, maybe Blender or Rhino or AutoCAD or SketchUp. You understand modeling, conventions, meshes, optimizations, etc., etc. Your approach for using that AI tool is very different. You're not just playing, you're having a goal now. You expect precision, control, and output that fits your pipeline. But the AI doesn't always cooperate. You can't tweak every detail, the mouse isn't watertight, and the prompt, oh my god, that's too vague. You get frustrated. This isn't just a toy. You want a partner in design, but instead, the AI feels like a black box. This contrast it is what we are studying. We designed a comparative user study where both casual and professional users are completing 3D modeling tasks using AI tools. We observed how they explored the interface and how they reacted to the results, where they got stuck, and how they tried to learn. We are not measuring success, we are understanding behavior, learning, and expectations. To do this, we are using two AI tools known as Meshi AI and Spline AI. So Meshi and Spline, they work with text or images input to generate 3D models. But it limits what users can do afterwards and use a credit system. So every generation costs something. Spline, on the other hand, is the most interactive canvas where you can click, move, tweak objects with AI support. These tools help us see how users behave under different constraints and freedom. Right now, we are deep in the research and we have interviewed and observed users from both the groups and coding their responses to understand emerging patterns. Our aim is not to rate the tool, but to unpack how different users learn, adapt, or sometimes get blocked when working with AI in their creative workflows. Next, we'll complete our interviews and finish our thematic coding. After that, we'll synthesize the findings to make concrete suggestions on how AI tools can better support both casual learners and experienced professionals without assuming one size fits all. So whether you are someone just starting out or someone who designs for a living, the way you interact with AI tool is meaningful. Understanding these differences help us design smarter, more supportive AI systems that meet people where they are. That's the vision behind this project. We're still looking for participants with experience in 3D modeling. So if you or someone you know has worked with these tools like Blender, Rhino, Fusion 360, etc., we'd love to hear from you. Well, it's just a one-on-one session. It's online, and participants receive a small honorarium. So you can just email me on my email, which is presented on the slide, and feel free to share this invite. Thank you so much. I'm ready to take any questions.
Thank you, Kanad. Do we have any questions? Okay, so we have one more presenter, because, well, our coordinator probably forgot to add his name onto the list previously. But let's welcome Justin Benoist. Which university?
From ETS.
From ETS. Okay, so if you have. That's yours?
Yeah.
Okay.
Hello everyone, I'm Justin Benoist, so first year PhD student at ETS. I try to keep it short because I know we are a bit over time and you must be a bit hungry right now. So my work is about, my current research is about neuroprogressive photon mapping. So usually in rendering, what we do is that we shoot a bunch of rays for millions of time, and we can get very realistic images at the end of the process. The only issue is that for like more complex light interaction, we can get images that are very noisy. And for example, for caustics, so caustics are very present in everyday life and they can be used for artistic purposes that can be interesting. So when we try to render them using traditional path tracing, for example, we can get very noisy images. So one way to render caustic is to use a technique called photon mapping. So for photon mapping, we start from the light, we shoot virtual particles called photon. They will bounce around the scene, deposit on surfaces, and at some point we can gather the created photon map to try to estimate the density of photons around the query point and get the final radiance of the pixel. So this way you can render good caustics. So to have the density of the photon, we use what we call kernel density estimation, KDE. And for KDE, we can use like simple kernel function, for example, Gaussian or cone kernel. And if we do that for millions of photons, we can get beautiful caustics compared to the path tracing approach. The only issue with path tracing is that when we zoom in a little, we can see some blur. It's because it's biased, because we need an infinite number of photons to get good accuracy for the caustics. So one way to solve this is to use progressive photon mapping. So for progressive photon mapping, we start with doing photon mapping with huge radius, and then we repeat the process with smaller and smaller radii. Another way to do that is to use deep photon mapping introduced in 2020. So instead of using a Gaussian or a cone kernel, we use a more complicated neural network that will be adaptive to the photon distribution. This way we can get better estimates. So this network predicts the weight for each photon that will be used for the density estimation. The only issue is that we have the same problems than with classic photon mapping, that is to say high memory consumption because we have infinite number of photons. We also can't use the progressive photon mapping algorithm with this algorithm because we are forced to use k-nearest neighbors. And also we are not normalized, so we get bias if we try to use it iteratively. So the goal of my current research is to kind of use the deep photon mapping advantages, so adaptive kernels, etc., with at the same time of progressive photon mapping. So for this, we introduced an architecture like this. So we encode the photon using simple neural network, then we create a kind of deep context vector that translates the photon distribution around the query point. And at the end, we predict a 2D anisotropic kernel so that we can scale and rotate this kernel in function of the photon distribution. And the advantage of using the 2D anisotropic Gaussian kernel is that it is normalized, so we can use it iteratively. So if we look at some results, we can see that using naively the deep photon mapping architecture on the left with the progressive scheme gives high error, as shown on the bright pixel of the error map. Our results are better than the classic SPPM results on the right. That is another classical progressive photon mapping approach. Overall, our results are better than SPPM. They are equivalent or better than CPPM, the state of the art. It depends on the scene. We get a low overhead. I don't want to go too much in the details, but we can reuse the encoded photon later to get better performance. And here are some better results. So here we can see, like, for example, the caustic created by the lump is sharper on the more we go to the right of the image, thanks to our method. So yes, that was it. Thank you all for your attention. And
Justin, do we have any questions for Justin? Okay, all right, so I guess this will be the end of our session. It goes a little bit over time because of some complications on the technical side. Sorry, it's during the summer, so it's very hard to find technicians. Let's thank all our presenters for sharing their work. And right, so starting from now, it's the lunch break. So our lunch will be like right in the lobby, and the next session will start from 1 p.m. in the same room. And so I'll see you guys in the afternoon. Thank you.